Good afternoon. I'm a researcher at the Open University, and I'm going to be talking about the analytical instrumentation for the ESA ISRU demonstration mission. This is a mission to demonstrate the use of the metalysis FFC process for the extraction of oxygen from lunar regolith. So the requirements of the mission are in total to produce 100 grams of oxygen from at least 5 samples. The advantages of it for the metalysis process that we're doing in lunar environment, which is a lower gravity, and also testing mechanisms. The resources is going to be for 1 lunar day only, and the total instrument mass is 4 kilograms. So in the process of trying to determine the efficiency of the ISRU process, we need to know the starting material, its elemental composition, to know how much oxygen there is, the mass of the sample, and then after the process, we need to know the oxygen concentration in the gas stream and the flow rate of the gas from the metalysis cell. We've assigned an error budget of relative accuracy of 10% for the total measurement. So for each of those subsystems, we've assigned an error budget, 7% for the solid analysis and 3% for the gas analysis. The instrumentation, we've chosen to try and be as much as possible standalone. So the instruments include their own power converters and processor data. So the instrument takes commands from the lander from ground, does its analysis, and then passes the data back to ground. The idea of this is that if there's any changes in the instruments or movement on different landers, we can accommodate those fairly easily without affecting the rest of the payload. The advantages in this is that testing is fairly straightforward in that the instrument can be tested without requiring other payload or lander systems to be available, and integration, hopefully, is more a case of bolting on, connecting power and comms interface. So for the solid sample analysis, we started off looking at XRD XRF instrument. This was developed for ExoMars. Unfortunately, it wasn't on the final payload. And it uses a radioactive X-ray source to generate X-rays, which is aimed at of diffraction rings detected by a CCD. So that gives you the mineralogy of the sample, and then the X-ray fluorescence from the same instrument will give you the elemental composition. So the graph on the right is the trace from the X-ray fluorescence, showing that you can detect most major elements all the way down to aluminium. The problem with this instrument we found is it's difficult to accommodate into the lander package, and it depends very much on getting the angle right to the sample, and the sample is being collected and loaded into a container. The height isn't always the same, and so it's very difficult to try and accommodate for differences in the sample that was collected. Also, it had a 10-hour analysis time because the radioactive source is very weak. And given that you need to analyze 5 samples and there's only 10 Earth days to do the mission, it was too short time to do all the analyses. So we looked at some alternatives. One is active X-ray spectrometry. This just uses XRF, looks down on the sample, uses an active source, so has a much higher sensitivity. All these instruments we listed here have an analysis time of a minute or less. So it's more in keeping with the timescale of the mission operations. That gives you the elemental composition. And then you've got 2 options for the mineral composition. Could either use SAMCAM, which is high TRL, is on the Prosper mission, or Micro Omega, which is larger and heavier, but has high TRL, having been on several missions already. Another alternative is to use a Libs-Raman instrument. Again, it was developed for ExoMars. It wasn't on the final payload, but its continued development has been progressed on breadboarding up to TRL6. It's also got the advantage that after the sample has been processed, the lasers can actually be used to vaporize the salt covering the sample, and you might actually be able to get the composition of the sample after the processing. Moving on to the gas analysis instrumentation, the requirements are to measure the oxygen concentration, but also to measure the composition of the gas from 10 to 150 mass units with a detection limit of 10 parts per million and a sample rate of 1 per minute. We're also interested in contamination on the oxygen supply, since we're going to be breathing this oxygen at the end of the day. Contaminants like hydrogen sulfide or sulfur dioxide, which would be coming from the lunar regolith, or hydrogen chloride or chlorine from breakdown of the salt. On the right is the European occupational exposure limits, and they're all of the order of 1 or 10 ppm at maximum level. And if you're using this as breathable air, you probably want 10 times less. So the contaminants are below the emission requirements. So we also considered instruments that may be able to measure that. So our main instrument is the mass spectrometer, ion trap mass spectrometer, got good heritage, small, low mass and low power. And you get spectrum there on the right, which gives you the mass range 10 to 150 unit resolution. Where we had to develop or more was the tunable laser spectrometer. So tunable laser spectrometry is very good at detecting specific gases. You usually use one laser per gas and has very high sensitivity. So we had some funding from the UKSA for a Disrupt project to look at using TLS for 3 target gases, SO2, H2S, and HCl. We actually found for SO2 and H2S, you could actually only needed 1 laser. So 2 lasers would actually give you those 3 gases. And theoretical calculations gave you that you could actually detect to below 1 part per million quite easily with a 22 centimeter gas cell having 100 reflections. So it's a 22 meter path length. So that's the design of the instrument. At the top is we combined the mass spectrometer and the TLS. They actually work very well together. They both scan a voltage and give you a spectrum out. So the actual same computer can actually operate both systems. We actually operate in a batch mode where sample is collected and then can be passed to the mass spectrometer or TLS. We have a calibration gas to do the high accuracy for the mass spectrometer. And the total mass of the system was 3.29 kilograms. Unfortunately, mass is a problem, and so with the mass reduction exercise for the whole of the payload, the mass had to be reduced, and the easiest thing to do with our modules is remove one module, and so the TLS was unfortunately removed to give the final design, which is just the mass spectrometer with calibration gas and gas distribution system. So that's the summary. Basically, the analytical instrumentation is XRD, XRF. We're still undecided between that and the AXS and SAMCAM, and the gas analysis is an ion trap very similar to the PITMs with a gas manifold and gas calibration system. Thank you.
Thank you.